So good morning one and all. So myself Jagadish Sharam, Assistant Professor, Department of CSC. Today um, I'm going to start the module 2. The first topic is digital transmission. So in this digital transmission, first we'll discuss about digital to digital conversion. Um, in this, we will see how to represent the digital data as digital signals and to convert this digital data into digital signal, we are going to use many conversion techniques like line coding, block coding, and scrambling. But for our syllabus, we have only the line coding technique. Um, uh, the topics we are going to cover in this particular digital to digital conversion is line coding. What is line coding? Basics of line coding. Then we're going to discuss about the line coding schemes, um, uh, such as polar, unipolar, Manchester, bipolar schemes. First, before going to the actual topic, mm, we need to know what is this digital to digital conversion. Why this digital to digital conversion is required? As we know, the computer can handle only the digital form of data, and whatever data we store in the computer, that is in digital form. So it is uh, necessary to convert the actual digital data into digital form so that it is easy to process at the computer side. First, we will discuss digital transmission. What is digital transmission? Data can be represented either in an analog or digital form. The computers used the digital form to store the information. Therefore, the data needs to be converted in digital form so that it can be used by a computer. Digital to digital encoding is the representation of digital information by a digital signal. When binary 1 and 0 generated by the computer are translated into a sequence of voltage pulses that can be propagated over a wire. So this process is known as digital to digital encoding. The name itself says digital data is converted as digital signal. That process is called as digital to digital encoding. So here how this particular line coding will help. So here it is being given here, converting a string of ones and zeros means digital data into a sequence of signal that is denoted by ones and zeros. For example, 1 can be represented as positive voltage and 0 can be represented as zero voltage or negative voltage. In the diagram, you can observe there is a sender and receiver, and at the sender side we have digital data that is 0101 dash 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 101. This particular digital data is encoded um, by the encoder, and after encoding, our digital data is converted as digital signal in voltage form. See, a 0 is represented as 0 voltage, whereas 1 is represented as positive voltage, and so on. And this digital signal is transmitted through the digital media or transmission link. You can observe here. Whereas on the destination side, the decoder will decode the digital signal into digital data form. So once we are getting the actual data, whatever is sent from the source side, and the receiver will receive the data. How we are going to map digital data symbols onto signal level. The meaning of this one is how the actual data is converted as signal levels. A data symbol can consist of a number of data bits. So it can be 1, 0, or single bit we can say, or it can be 2 bits, that is 1 1 1 0 0 1 0 0 and so on. The data symbol can be coded into a single signal element or multiple signal elements. Example, 1 can be represented as positive voltage and 0 can be represented as negative voltage. Sometimes your data value 1 can be represented either positive voltage or negative voltage, or your 0 can be represented as negative voltage or positive voltage. The ratio small r is the number of data elements carried by a signal element. Small r is the number of data elements carried by a signal element. Relationship between data rate and signal rate. The data rate defines the number of bits sent per second, BPS, bits per second we say. It is often referred to the bit rate. Bits per second or bit rate we say. This is with respect to the actual data. Whereas signal, once if we convert the data into signal, the signal rate will appear. The signal rate is the number of signal elements sent in a second and is measured in bars. It is also referred to as the modulation rate. It can be measured in bars, and it is also referred to as modulation rate or signal rate we can say. So the goal of this particular thing is to increase the data rate while reducing the baud rate. We need to increase the data rate and by reducing the baud rate or signal rate we can say. Here we can see signal element versus data element. Here we have the data element for one signal element. Small r is equals to 1. So already we discussed this one. R is equals to 1. Rate. One data element per pulse. One data element per pulse. We have the input data 101. To represent each bit, one particular pulse is used. One particular signal is used to represent the actual data. That is what the meaning. Whereas in the second diagram, one data element per two signal elements. To represent one data element, two signal elements are used. If you can observe, um, one is represented with the two signal elements. In the actual pulse, it has been divided into two parts. So small r is equal to 1 by 2. Here, third one, two data element per one signal element. Here, to represent two data elements, one signal element is used, whereas the four data elements to represent four data elements, three signal elements are used. So in the diagram, you can observe. So small r is equal to 4 by 3. So data rate and baud rate. The formula, the baud or signal rate can be expressed as capital S is equals to C into N into 1 by R baud, where N is the data rate, small c is the case factor, it can be worst, best, average, small r is the ratio between data element and the signal element. Here we have the problem on this particular. Yes, a signal is carrying a data in which one data element is encoded as one signal element. So small r is equals to 1. If the bit rate is if the bit rate is 100 kbps, what is the average value of the baud rate if C is between the 0 and 1? You can observe, we assume that average value of C is 1 by 2. The baud rate is then calculated as capital S is equal to C into N into 1 by R. Here C is equal to, it is assumed 1 by 2 um, into capital N. So that is nothing but bit rate is 1000 kbps. So 1000 kb, sorry, 100 kbps. 100 kbps is 100 into 1000. It becomes um, 1 lakh into uh, 1 by r. R value is 1 here, so 1 by 1. So totally 50 kilobaud is the answer. So note, although the actual bandwidth of a digital signal is infinite, the effective bandwidth is finite. There is one more problem. The maximum data rate of a channel is, as we discussed in the module 1, um, it is called as Nyquist formula. Capital N max is equal to 2 into B into log 2 L. Um, does this agree with the previous formula of N max is asking? A signal with L levels actually can carry log 2 L bits per level if each level corresponds to one signal element and we assume the average case is small c is equal to 1 by 2, then we have n max is equal to 1 by c into b into r, so is equal to 2 into b into log 2 l. Consideration for choosing a good signal element refers to as line encoding. Here you can observe we need to consider some of the points here. Baseline rendering. A receiver will evaluate the average power of the received signal called the baseline. A receiver will evaluate the average power of the received signal. The as we have seen in the diagram, the sender will send the data in the form of data signal to the receiver, while at the receiver will evaluate the average power of the received signal called baseline and use that to determine the value of the incoming data element. Baseline rendering, it is used to determine value of the incoming data element. If the incoming signal does not vary over a long period of time, the baseline will drift and thus cause error in detection of incoming data element. This is called as baseline rendering. So in shortly we can say that once the signal is received by the receiver, the receiver will evaluate the average power of the received signal. If the received signal does not have the proper power, it may lead to baseline drift. Drift means drop will happen, and it will cause the error in detection of. It will cause the error. So a good line encoding scheme will prevent long runs of fixed amplitude. So now we are understanding why this particular line encoding techniques are. A good line encoding scheme will prevent long runs of fixed amplitude. It will try to maintain the long runs of the amplitude. So next is first we have seen that baseline rendering, first element. Um, Next one is DC component. When the voltage level remains constant for a long period of time, there is an increase in the low frequency of the signal. So most channels are band pass and may not support the low frequencies. Here, when the voltage level remains constant for a long period of time, there is an increase in low frequency of the signal. Whatever the signal is received at the receiver side, when the voltage remains constant for a long period of time, it leads to low frequency of the signal. Such low frequency signals are not supported by the band pass channels. So this will require the removal of DC component of a transmitted signal. So the meaning of this one is DC component should be removed from the actual signal. Third component is self-synchronization. The clocks at the sender and receiver must have the same bit interval. If the receiver clock is faster or slower, it will misinterpret the incoming bit stream. So you can observe here in the diagram. So actual information sent is 10110001, while at the receiver side it is received as 110111000011. So there is a misinterpretation is happening due to the uh, uh, no proper self synchronization. So here, based on this self-synchronization, there is a problem. In a digital transmission, the receiver clock is 0.1% faster than the sender clock. Receiver is faster than the sender clock. How many extra bits per second does the receiver receive if the data rate is 1 kbps? How many if the data rate is 1 mbps? Solution: at 1 kbps, the receiver will receive 1001 bits per second instead of 1000 bits per second. You can observe actual speed is what? 1000 bits sent, and it is received as 1001 bits received. And what is the extra bits? 1 extra bits per second is happened. So in the same way, for 1 mbps, the receiver receives 1001,000 bits per second uh, instead of 10 lakh bits per second. It is receiving 10 lakh thousand bits per second. Instead of receiving 10 lakh bits per second, it is receiving 10 lakh thousand bits per second. So actual sent is what? 10 lakh bits sent, and actual received is what? 10 lakh thousand bits received. So extra bits are 1000 here. So this is due to the uh, uh, change in the synchronization. So there is no proper synchronization between the sender and receiver. So here some of the things we need to discuss about the line encoding. Error detection. Error occur during transmission due to line impairment. Your encoding scheme should support for the error detection capability. So error detection, why the error will occur in the actual signal means, so this will happen due to the line impairment. Line impairment is nothing but due to the noise, due to the attenuation in the transmission path it will happen. Some codecs are conducted such that when an error occurs, it can be detected. For example, a particular signal transition is not part of the code. When it occurs, the receiver will know that a symbol error has occurred. Please concentrate on this particular statement. Some codecs are constructed such that when an error um, occurs, it can be detected. For example, a particular signal transition is not part of the code. When it occurs, the receiver will know that a symbol error has occurred. This particular transition will see in the next example. Noise and interference. There are line encoding techniques that make the transmitted signal immune to noise and interference. Even some line coding techniques will support for the noise and interference immunity. This means that signal cannot be corrected. It is stronger than error detection. Complexity. The more robust and resilient the code, the more complex it is to implement, and the price is often paid in baud rate or required bandwidth. So till here we have discussed about the line coding techniques, what are the uses of the line coding, how the line coding techniques are useful, Now we will see different line coding schemes here. Here we have different line coding schemes such as unipolar, polar, bipolar, multi-level, and multi-transition. For our syllabus, we have only unipolar, polar, and bipolar schemes. We will discuss one by one. All signal levels in the unipolar, all signal um, in the unipolar encoding uses only one voltage level. That is, ones are encoded as positive value and zeros are encoded as zero value. Yeah, you will see in the example. Here, all signal levels are not one side of the time axis, either above or below. Here in this we have unipolar NRZ scheme. You will see that what is that NRZ? Non-return to zero scheme is an example of this code. The signal level does not return to zero during a symbol transmission. We will see in the example. Scheme is prone to baseline wandering. Here already we discussed some of the component elements um, about the data signal. Scheme is prone to baseline wandering and a DC component. It has no synchronization or any error detection. It is simple but costly in power consumption. The meaning of this one is it is prone to baseline wandering. Already we discussed what is baseline wandering, and also it is prone to DC components, and there is no proper synchronization, and it won't detect any sort of errors, and it is very costly and it consumes more power. We will see unipolar another scheme here. Example, the input symbols are 10110. Once if I convert these data symbols as data signals, it becomes, as we discussed, unipolar NRZ. Only the bit 1 is represented as positive voltage, whereas 0 is represented as 0 voltage, whereas 1 is represented as positive voltage. Next one is also represented as positive voltage, and 0 is represented as 0 voltage. So here, how the power is calculated, you can observe half into V square plus next bit is 0, half into 0 square, so half into V square. In this way, unipolar NRZ scheme will work. So after this section, I am going to give some of the assignments to solve the problems on these line coding schemes. Next, we'll go for the polar NRZ scheme. Polar NRZ scheme. So before going to polar NRZ, what is polar? We need to understand. Polar encoding uses two voltage levels, that is positive and negative. There are four types of commonly used polar encoding schemes here: NRZ, RZ, Manchester, and differential Manchester. We'll see one by one. First, we need to understand um, how these polar symbols, polar signals are represented. The voltages are both sides of the time axis. As we see in unipolar, only the voltages are at the one side, and here in this polar and polar scheme, the voltages are at the both the sides, that is positive and the negative side. We'll see in the diagram in the example. Polar enhancement scheme can be implemented with two voltages. For example, to represent one, positive voltage is used, whereas to represent zero, negative voltage is used. In this polar NRZ, we have two versions. One is NRZ level, or shortly NRZ hyphen L, And one more is NRZ inversion, shortly NRZ hyphen I. NRZ level L, positive voltage for one symbol and a negative voltage for other, negative for the other, you will see in the example. And another inversion, the change or lack of change in polarity determines the value of a symbol. For example, a one symbol inverts the polarity of a zero, polarity a zero does not. You will see in the example. You can observe NRZL, the input data symbols are 0 1 0 1 0 1 1 1 0. How this NRZL will work, we'll see. Okay, it is starting from the positive voltage and it is moving towards the negative voltage. Whereas next we have the one input symbol, the symbol. So it is moving from negative voltage to the positive voltage. And next we have the zero, same, it is moving horizontally from positive voltage to the next positive voltage, from positive voltage to the next positive voltage. Since the next symbol is also zero, next symbol is one, so it is moving from positive voltage to negative voltage and it is taking the uh, transition here. And next also one, so it is moving horizontally from negative voltage to negative voltage. Next is also one, it is moving from negative voltage to negative voltage, and the next symbol is zero, so it is taking the transition from negative voltage to positive voltage. In this way, the NRZL will work. So NRZL will say that um, non-return zero encoding uses either positive or negative signal. In NRZL encoding, the level of signal depends on the type of bit that is that it represents. Here you will see with respect to the NRZI inversion. Um, Here you can observe since the symbol first symbol is zero, so it is taking the it is moving from positive voltage to the towards the negative voltage. So here halo circle represent the no inversion, and filled circle represent the next bit is one, means inversion. You can observe zero is taking from the positive voltage and is moving towards the negative voltage. Since this particular filled circle represents the inversion, so why the inversion it will take means because next bit is 1, so it should take the inversion, so it is taking the inversion. Next bit is 0, so no inversion is required, so it takes the horizontal transition, you can observe here. And next bit is also 0, it is taking the horizontal transition. Since the next bit is 1, it should take the transition inversion, it should take the inversion. Here it is moving from negative voltage to the positive voltage. Next bit is also 1, so it is moving from positive voltage to negative voltage, and next bit is also 1, so it should take the inversion. So in this way, whenever the symbol 1 appears, it should take the inversion. Mm. And you can observe next bit is 0, it is taking the horizontal. So in this way, it will um, uh, represent the actual data symbol in data signal. And you can observe, so how much bandwidth is required, what is S value, what is the R value, we will discuss in the next. So note, in NRZL, the level of the voltage determines the value of the bit. NRZI, inversion or lack of inversion determines the value of the bit. NRZL and NRZI both have an mm, average signal rate of n by 2 bar. So for every scheme, these elements are very important. We need to consider. For NRZL and NRZI both have an average signal rate of n by 2 bar. And some of the points he has given, NRZL and NRZI both have a DC component problem. We need to focus here. And baseline wandering, it is worse for NRZL. Here baseline wandering is very worse for the NRZL. For both NRZL and NRZ high have no self-synchronization capability and no error detection capability. Both are relatively simple to implement. So we will see um, a problem here. A system is using NRZ high to transfer 1 Mbps data. What are the average signal rate and minimum bandwidth? The average signal rate is capital S is equals to C into N into R is equals to 1 by 2 into capital N into 1 is equals to 500 kilowatt. The minimum bandwidth for this average baud rate is B minimum is equals to minimum bandwidth is equals to capital S is equals to 500 kilohertz because um, the frequency is represented in hertz. Okay. Note small c is equals to 1 by 2 for the average case, and for worst case it is 1, and for best case it is 0. Next we discuss about the polar RZ. So already we discussed about the polar NRZ. Once again in polar NRZ we have the polar NRZL, polar NRZI. Next is polar RZ. First we need to differentiate what is RZ and NRZ. You will see. NRZ means non-return to zero. Your transition will not move to the will not return to zero in the case of NRZ. Whereas in RZ it will move to the here return to zero uses three values, whereas in NRZ it will use the two values, that is positive voltage and negative voltage. Um, Whereas uh, without returning to the zero. In the case of NRZ, polar NRZ, it will take only the two values, that is positive voltage, negative voltage, and it will not return to zero. That is why its name is NRZ. Whereas in polar RZ, it will return to zero. So this will use three values, that is positive, negative, and zero. Um, the RZ encoding provides synchronization information. Here you can observe the RZ scheme uses three voltage values, positive, 0, and negative. Each symbol has a transition in the middle. You will see that either from high to 0 or from low to 0. This scheme has more signal transition, 2 per symbol. There is a more signal transition. We will see what is the transition in the example. 2 per symbol, and therefore require a wider bandwidth. Since there is a transition, so we require the more bandwidth. No DC components or baseline wandering. Here, there is no DC component and baseline wandering in the case of um, polar RZ. Self synchronization. Transition indicates symbol value more complex as it uses the three voltage levels and has no error detection capability. These are all about the polar RZ. You can observe here the example. The input symbols are 0, 1, 0, 0, 1. See here how the 0 is represented. You can observe it is starting from the negative voltage in the exactly in the middle of the pulse. It is taking the transition and it is moving towards the positive voltage. So as we discussed already, in the polar RZ, it will go for the transition. What is the transition? Transition is nothing but whenever we represent a symbol in the middle of the pulse, the signal will take the transition. You can observe in the exactly half of the pulse, it is taking the transition. It is moving to the towards the positive voltage to represent the value 0. Whereas to represent a value 1, It is starting from the positive voltage and it is taking the transition exactly in the middle of the pulse and it is moving towards the negative voltage. Whereas to represent a, so here in this, okay, next we have the bit zero. Here, how we are going to, it is starting from the negative voltage and it is moving towards the zero. Here, it is moving towards the zero. So in polar RZ, three values are used. Your actual data symbol is represented in three values: positive voltage, negative voltage, and zero. Here, this is how it is returning to zero. This is what we say, returning to zero. Whereas in polar NRZ, it is this was not there. It was not, your signal was not returning to zero. Whereas in polar RZ, your signal is returning to zero. You can observe. Clear? So since the symbol is zero, it is starting from negative voltage. It is taking the transition exactly in the middle of the pulse, and it is moving towards the here. So why it is moving towards the negative means because next value is zero, so it is moving towards the negative voltage. So here in this example, in this particular bit, since the next value is 1, so it is moving from zero value voltage to the positive voltage. Whereas here also, why it is moving towards the negative voltage? Because this value is 0, so it is moving towards this one. So whereas next bit is 0 here, so it should move towards the negative voltage. So it is moving towards the negative voltage. Since the next value is 1, so from the 0 voltage it is moving towards the positive voltage and it is taking exactly transition at the middle of the pulse and it is moving towards the 0 voltage. So this is how this polar RZ scheme will work. And here you can observe in the graph, its rate is 1 by 2 and yes, average is equal to n and it require more bandwidth as is shown in the diagram. Um, okay, uh, here we will stop till the polar NRZ and the polar RZ. In the next video, we will discuss about the polar Manchester and the differential Manchester encoding scheme. Till then, go through the video and try to analyze the line encoding technique and I will give some assignments, solve them and reply back with the solution. So kindly make use of these videos. Thank you. Thank you. Bye.